Welcome back to Basic Electronics. In this lecture, we will figure out the contribution of a pole and a zero to the magnitude and phase Bode plots. We will also consider some other terms. Once we know these contributions, it is a simple matter to add them and obtain the overall Bode plot. So let us start. What we have done so far is to look at a sample transfer function h of s or h of j omega and look at its magnitude and phase plots versus omega in radians per second or f in hertz. Let us now consider a generalized transfer function h of s and see how its Bode plots, that is the approximate magnitude and phase plots, can be constructed. Here is a general expression for h of s. In the numerator we have k 1 plus s by z1, 1 plus s by z2 and so on. In the denominator we have 1 plus s by p1, 1 plus s by p2 and so on. Now these quantities minus z1 minus z2 etc. are called the zeros of h of s. For example, if I substitute s equal to minus z1, this bracket becomes 0 and h of s becomes 0. The quantities minus p1 minus p2 etc. are called the poles of h of s. If we substitute s equal to minus p1, for example, then this bracket becomes 0 and h of s becomes infinity. In addition, there could be terms like s and s squared in the numerator, and we will see later how to handle those as well. We will assume for simplicity that the zeros and poles are real and distinct. So a given 0, for example z1, does not appear more than once. Similarly for poles. And they are all real. In reality they actually could be complex, but to make things simple we will assume that they are all real. Now what is the construction of the Bode plots involve? A. Computing approximate contribution of each pole or zero as a function of omega. That means we look at the contribution of this term to h of s, we look at the contribution of this term to h of s and so on. And B. Combining the various contributions to obtain mod h and angle h versus omega. So once we know the individual contributions, like the contribution from this term and so on, we then combine all of those contributions to obtain the net mod h and angle h versus omega plot. Let us take some examples and see how this can be done. Let us start with the pole. Here is a transfer function with a single pole 1 over 1 plus s by p, where p is a real and positive number 10 raised to 3 radians per second. So this system has a pole at minus 10 raised to 3 radians per second, going by the definition that we saw earlier. Alright, now let us rewrite h of s as h of j omega, that is 1 over 1 plus j omega by p, and the magnitude of h of j omega is 1 over square root of 1 plus omega by p whole squared. And we now want to plot the magnitude of h as a function of frequency, and as we said before, we will plot mod of h in dB on a linear scale versus frequency on a logarithmic scale. And for reference, let us mark this magnitude of the pole, which is given by this positive number p over here, and that is 10 raised to 3 radians per second. A Bode plot is essentially an asymptotic plot So what do? We plot the given function in certain limiting cases, and that gives us the asymptotes, and then we put these asymptotes together to obtain the overall picture. Alright, so let us begin with asymptote 1. That corresponds to omega much smaller than p, and when that happens, this term becomes negligibly small and mod h approaches 1. And in terms of dB, of course, it is 0 dB because 20 log of 1 is 0. So that is asymptote number 1, and that is what it looks like. 0 dB for omega much smaller than p. Now if you notice, we have actually extended this asymptote all the way up to p, because we are only interested in an approximate description of the function. Obviously there is going to be some error at this point, because this point is omega equal to p, not omega much smaller than p. Our asymptote 2 corresponds to omega much greater than p, and in that case this term is much larger in magnitude than this one, so we ignore this one here, and the magnitude of h then is 1 over omega by p, or p by omega, and h in dB is then 20 log of p by omega, that is 20 log of p minus 20 log of omega. This is a straight line in this plane, and it has a negative slope, so it's going to go like that. Furthermore, if omega is equal to p, then this term and this term are equal, they cancel each other, and h is 0 dB. So for omega equal to p, our h is going to be 0 dB. That is precisely this point here. So we are going to have a straight line passing through this point with a negative slope, and now let us see what that slope should be. Let us consider two values of omega, omega 1 and 10 times omega 1. For example, omega 1 could be 10 raised to 4, and 10 times omega 1 is then 10 raised to 5. For the first omega, omega 1, h1 is 20 log p minus 20 log omega 1 from this expression. For the second case, h2 is 20 log p minus 20 log of 10 omega 1, because omega 2 is 10 omega 1. Now if we take the difference between these two, we get h1 minus h2 as minus 20 log of omega 1 divided by 10 omega 1. This term cancels. What is omega 1 by 10 omega 1? It is 1 over 10, and log of that is minus 1. So minus 1 times minus 20 is plus 20. So that is 20 dB. So what it means is h for omega 1 is going to be higher than h for omega 2 by 20 dB. In other words, if the frequencies are apart by 1 decade, omega 1 and 10 times omega 1, then h is going to be different by 20 dB. This is the same as saying that h versus omega has a slope of minus 20 dB per decade. This decade refers to this factor of 10 here in omega, and this 20 dB refers to this difference of 20 dB in h. So the slope that we are going to observe for this straight line is going to be minus 20 dB per decade. So that is what our asymptote 2 looks like. It passes through this point, omega equal to p and h equal to 0 dB as we discussed, and also it has a slope of minus 20 dB per decade. So if we go up in frequency by 1 decade, we come down in h by 20 dB. That is why this minus sign here. Alright, now at omega equal to p, if we look at this exact expression, what is the magnitude? this becomes 1 because omega and p are equal. So we have 1 plus 1. So that is 1 over square root 2. So the actual value of h is 1 over root 2, and if we convert that to dB, it turns out to be about minus 3 dB. So definitely at this point there is going to be that much error. What we have done is shown 0 dB here, but the actual value is minus 3 dB. Like that. So this is the blue one is our exact mod h versus frequency curve, and there is definitely some error at this point as we suspected, but asymptotically it shows excellent agreement as we go away from this pole in both directions, and that is the power of the Bode approximation. We will do that for other functions, and then we will see how to put together the different contributions to obtain the Bode magnitude plot for a more complex function. Let us now look at the Bode phase plot for this same transfer function 1 over 1 plus s by p, which corresponds to a single pole, and the pole is at minus 10 raised to 3 radians per second as in the previous slide. Alright, now as we have seen before, we plot the phase on a linear axis and frequency on a logarithmic axis. And once again, for reference, we will mark the magnitude of the pole over here, that is 10 raised to 3 radians per second. The angle of h is given by minus tan inverse omega by p, and that follows from this equation here. And let us now see how to obtain the asymptotic Bode plot for the phase. Let us start with asymptote 1, which corresponds to omega much smaller than p, and by this what we mean is omega less than p by 10. This is our p by 10 is here, so we are talking about this range over here. With this condition, omega by p is going to be less than 0.1, and as an approximation we say that angle of h is nearly 0 because this is a small number. Alright, so that gives us asymptote 1. So angle of h is 0 in this range here, that is omega less than p by 10, and that is what it looks like. Let us look at the second asymptote now, which corresponds to omega much larger than p, say omega greater than 10 times p. This is our p, 10 times p is here, so we are talking about this region here. Alright, now what happens if omega is much greater than p? This 1 is small compared to omega by p and can be ignored, and therefore h of j omega is approximately 1 over j omega by p, and the phase of this function is simply minus 90 degrees or minus pi by 2, and that gives us the second asymptote. So for omega in this region, the phase is minus 90 degrees, and that is the second asymptote. Let us now look at the third asymptote, which corresponds to p by 10 less than omega less than 10p. This is our p by 10. This is 10 times p, so we are talking about this region here. Alright, now in this region we assume that the angle of h varies linearly with log omega. That means we have a straight line connecting these 2 points, and that is our third asymptote. Now let us look at what happens at this frequency omega equal to p. What is the phase given by this expression? Omega equal to p, that means we have minus tan inverse of 1, that is minus 45 degrees. This is our asymptote 3, a straight line connecting these 2 points, and notice that the asymptote also passes through minus 45 degrees at omega equal to p. Alright, let us now compare the Bode approximation with the exact result. the one given by the blue curve here. At omega equal to p, the two agree. They both give minus 45 degrees. As we move away from the pole, the agreement between the two is excellent in that direction as well as in this direction. Next, let us consider the contribution of a zero, and we will first consider the magnitude Bode plot. Here is an example, h of s equal to 1 plus s by z, where z is 10 raised to 3 radians per second. And if you recall, this means that our 0 is at minus 10 raised to 3 radians per second, following the definition that we looked at earlier. Alright. Now, as before, we will plot mod of h in dB on a linear scale versus omega in radians per second on a logarithmic scale, as shown here. We can rewrite h of s as h of j omega 1 plus j omega by z, and from that we obtain the magnitude of h as 1 plus omega by z squared. Alright. Now, as we did in the case of the pole, we will take two cases. Case 1, which gives us the first asymptote, omega much less than z, and in this case we can ignore this term, and our h of j omega then approaches 1, mod of h approaches 1, this term being very small. And what does that mean? That means mod h in dB is 0 dB. So here is our first asymptote, 0 dB here, and although this applies to omega much smaller than z, we will extend that all the way up to omega equal to z, because we are seeking an approximation. Alright, now let us take the second case, in which omega is much greater than z. That gives us the second asymptote. With this condition, we can ignore this 1 with respect to omega by z squared, and then mod of h becomes simply omega over z, like that. And then in terms of dB, mod of h is 20 log omega minus 20 log z. Now this is a straight line in this plane here, and let us make a couple of observations about this straight line. First, if omega is equal to z, then this first term cancels with the second term, and we get h equal to 0 dB. That means this straight line is going to pass through this point, that is omega equal to z, mod h equal to 0 dB. Point number 1. Point number 2, the slope of this line is going to be 20 dB per decade, because we are plotting h in dB versus log of omega, and this number then gives us the slope. We can also figure out the slope by considering two values of omega, namely omega 1 and 10 times omega 1, that is two values of omega which are 1 decade apart. Alright, now for the first omega value, that is omega 1, mod h in dB is 20 log omega 1 minus 20 log z from this equation. For the second value of omega, that is 10 times omega 1, mod of h in dB is 20 log 10 omega 1 minus 20 log z. We will call this as mod h in case 1, this one as mod h in case 2. Now if we take the difference between these two, h1 minus h2, what we get is 20 log omega 1 divided by 10 omega 1. This term cancels. This omega 1 cancels, and therefore we get log of 1 by 10, which is minus 1, and therefore h1 minus h2 turns out to be minus 20 dB. In other words, h2 minus h1 would be plus 20 dB. Alright. What it means is, as we go from some omega 1 to 10 times omega 1, we go up in h by 20 dB, and that is why the slope is 20 dB per decade. Alright, let us now look at the asymptote. That is what it looks like. It passes through this point, omega equal to z, h equal to 0 dB, and it has a slope of plus 20 dB per decade. If we change the frequency by a factor of 10, we go up by 20 dB. What about at omega equal to z, our asymptotes predict that h is 0 dB, but the actual value of course is different, and that turns out to be square root 2 from here. All we need to do is to put omega equal to z, so that becomes 1, and we have square root of 1 plus 1, that is square root of 2. 20 log of square root 2 is 3, so therefore h corresponds to 3 dB at omega equal to z. So that is the actual value of h, and therefore the exact curve looks like that. This difference is 3 dB. So there is of course some error, but asymptotically we see that the Bode approximation works really well as we move away from the 0 in either direction, either in that direction or in that direction. Let us now look at the phase plot for the same h of s, 1 plus s by z, that is 1 plus j omega by z, which gives us the angle as tan inverse omega by z. And once again we will take the same value of z, that is 10 raised to 3 radians per second. The frequency is on a logarithmic axis and the phase is on a linear axis. This is our z value. Alright, now let us start with asymptote 1, which corresponds to omega much smaller than z, say omega 10 times smaller than z. In this case, this is our z, 10 raised to 3. So z by 10 is here. So we are talking about this region here. What is angle of h in this case? So this is tan inverse 0.1 or smaller, and we will approximate that as 0. So that is our first asymptote. The phase is 0 up to z by 10, that is 10 raised to 2 radians per second. Asymptote 2 now, which corresponds to omega much larger than z, say omega greater than 10z. This is z, this is 10z. So we are talking about this region now. What happens if omega is much larger than z? Omega by z becomes infinity. Tan inverse of infinity is pi by 2 or 90 degrees. And as an approximation, we say that that corresponds to this entire region. Alright, so that gives us asymptote 2. Asymptote 3 applies to this region in between. And again, as we did in the case of the pole, angle h is assumed to vary linearly with log omega in this region. So what we do is simply connect these two points with a straight line. And at omega equal to z, that straight line will predict plus 45 degrees. And that is also the exact value of the angle, because at omega equal to z this becomes 1 and tan inverse of 1 gives us 45 degrees. So that is our asymptote 3, and the blue curve is the exact angle h. Once again, asymptotically it is in excellent agreement with our Bode approximation in either direction, either low frequencies or high frequencies. And at omega equal to z, our approximation also predicts the exact value of the angle. Let us now look at the contribution of a term like k, just a constant, or s, which is j omega, and s squared, which is j omega squared. Let us take h equal to k first, just a constant. What is 20 log h? It is 20 log k, and that is a constant. What about the angle? Let's say k is a positive constant. In that case, the angle is 0. If it's negative, the angle is 180 degrees or minus 180 degrees. What about h of s equal to s? Rewrite that as h of j omega equal to j omega. The magnitude is simply omega, and h in dB is 20 log of omega. So this is a straight line in our h versus log omega plane when h is plotted in dB. How do we figure out the slope? Let omega go from omega to 10 omega. What happens to log omega? It goes from log omega to log omega plus log 10. So this part will go from 20 log omega to 20 log omega plus 20. That is, the h magnitude will go from the old value of h plus 20 dB. So that means the slope is plus 20 dB per decade. So this is a straight line in the h versus log omega plane with a slope of 20 dB per decade passing through 1 0, omega equal to 1, h equal to 0. If we put omega equal to 1 here, then 20 log of 1 is 0, and that is why we say that this line must pass through omega equal to 1, h equal to 0 dB. Alright, so that is a plot. At omega equal to 1, which is this point, our h in magnitude is 0. That is the same as mod of s here. And as we increase the frequency, the function goes up with a slope of plus 20 dB per decade. Is this an approximation? Not really. This is actually the exact behavior of mod of h. We have not really made any approximation. Okay, now let's look at the angle of h. What is h of j omega? It is j omega. Omega is a real positive number. So the angle of h is simply angle of j, which is pi by 2 or 90 degrees. And that does not depend on what omega it is. It's a constant. Alright, let's now consider h of s equal to s squared, or h of j omega equal to j omega squared, which is minus omega squared. And the magnitude then is omega squared, and h in dB is 40 log omega. 20 log of omega squared, so that turns out to be 40 log omega. Once again, we go through this exercise of allowing omega to go from omega to 10 omega, and then we find that h increases by 40 dB. So therefore the slope is 40 dB per decade. So it's a straight line in the h versus log omega plane where h is in dB with a slope of 40 dB per decade and passing through omega equal to 1, h equal to 0 dB. Once again, put omega equal to 1 here, we get 0 dB, like that. So this is our omega equal to 1, so that passes through 0 dB, and this line has a slope of 40 dB per decade. When we go up in frequency by 1 decade or 1 order, we go up in mod h by 40 dB, 80 minus 40, 40 dB here. What about the angle? H of j omega is minus omega squared, is some negative number, and therefore the angle is 180 degrees, and that is irrespective of the frequency value. We can write this pi as either pi or minus pi, plus minus 180 degrees. In summary, we have seen how various terms such as a pole, a zero, a constant, etc. can be represented with Bode plots. In the next lecture, we will take an example and construct the overall magnitude and phase Bode plots using the individual contributions. See you in the next class.